Alright, so for our final video in Chapter 9, we're going to talk in more detail about Hess's law. This is one of the greatest ideas really in chemistry and physics in the 1800s. This idea that the overall change in enthalpy for a chemical reaction is equal to the sum of the enthalpy changes for the individual steps in a reaction. And this has become used in all kinds of different physics, chemistry, biochemistry, biology, in order to predict and explain the amounts of energy that are seen in particular reactions. Now, the problems that we'll need to work for this idea are a bit more detailed and require a bit more board space or screen space than we probably want to do in a video. So please come to class over the next few days because we're going to be working some of these in class, and then you'll be working some as well. But what's going to get us to some of these kinds of problems is a table that we'll find not only in the chapter 9 in our book, but chapter 8 in this older book I got this information from. These are the energies of reaction for making these, the enthalpies of reaction for making 1 mole of each of these substances from the elements at standard state. So we'll write out those reactions and see what that means, and then see how we can use these numbers to calculate delta H's based on Hess's law for reactions other than forming compounds from their elements at standard state. And the way that will work out is that the delta H for any reaction will be the sum of the delta H's of formation for all the products minus the sum of the delta H of reaction for all the reactants. And in fact, let me put the summation signs in there. Alright, so that's a better representation. The sum of the delta H's of formation for all the products minus the sum for all the reactants. All right, we can do something similar with heats of combustion. And we'll talk about, we'll do some examples in class on how that works as well. And you can start to look at these in the Hess's law and heats of formation, heats of combustion section of the chapter if you'd like ahead of time. But what these are defined as is the amount of energy required or given off in most cases. Negative numbers refer to energy given off for burning 1 mole of these items. By burning we mean reacting it with oxygen. So these are in kilojoules per mole or per gram or per milliliter if we're looking at liquids or solids. Now the final part of this chapter talks about entropy and free energy. As it turns out, delta S, which is change in entropy, and delta G, which is change of free energy, are also state functions, as is delta H, and that means that they're all going to obey Hess's law. They're all going to be able to have Hess's law applied to them. And so all these applications of Hess's law apply not only to delta H, but to entropy, delta S, and to free energy, delta G. Let's go ahead and define those. A process, a spontaneous process, is a process that once it gets started proceeds on its own without any continuous external force. So if I light a piece of wood on fire, it's going to burn as long as there are wood molecules that can get oxygen to them. It's a spontaneous process. Entropy is the amount of molecular randomness in a system. And we bring this up at the same time that we talk about spontaneous processes, because reactions are more spontaneous, more likely to be spontaneous, if entropy increases. When you think about this, your room becomes messy spontaneously. It doesn't become clean spontaneously. It's why we have to constantly put effort into cleaning our rooms and our houses. Messiness is natural. It is the spontaneous process in nature. So if we see an increase in entropy or a decrease in enthalpy, so a process being exothermic, giving off heat energy, giving off enthalpy, is also pushing toward a process being spontaneous. And a scientist named Gibbs in the 1800s developed this into an equation that can be used to predict numerically, mathematically, whether any process is going to be spontaneous. And he said delta G, the Gibbs free energy of a process, is going to be delta H for that process minus the temperature in Kelvin times entropy. Temperature has to be in Kelvin because anytime we're multiplying by temperature, it needs to be in Kelvin. But what we'll notice, for example, melting for water, for ice, is spontaneous at temperatures that are larger than 0 degrees and not spontaneous at temperatures that are smaller than 0 degrees. So that's where the temperature factor comes in. Melting makes the molecules more disorganized. So in that sense, melting should be a spontaneous process, but we have to put energy in. Delta H is positive, and so that hurts the process being spontaneous. So right at 0 degrees, 273 degrees Kelvin, is where delta H and T delta S for that process are equal, and you can see that in the math below here. And so that is the temperature at which melting for ice goes from being non-spontaneous to spontaneous. So if we think about that, if a process is endothermic, it's only going to be spontaneous at higher temperatures, because this term will dominate at high temperatures. If a process is exothermic, but it causes more organization to the molecules, then the opposite would be true. All right, so here's the list of problems I want you to take a look at. And I know you won't get these all done on the first day we work the chapter, but we're going to do some examples over the next few days, and then we're going to work some of these problems, and then we'll try some quiz problems out to see how well you're set up. So have fun, and please take a look at these.